Alright folks, hope you're warm and enjoy your days off here. Today it's going to be a couple of videos on Coulomb's law. The first one is going to lay it out. The next one will work a couple examples, and then you'll pretty much be able to rock it with problem set 2, chapter 25. Problem set 1, give it a go. You guys did a good job in the static electricity lab today. We talked about what we needed to talk about, very conceptual, deep thinking with what the electrons are doing. And then at the end we added in numerically how to quantify charge, units of coulombs, variable Q. That gets you through problem set 1. I want to get you through problem set 2, and then maybe in about a day's time I'll do a little electric field lecture, problem set 3. And I'm sitting with the hand we've been dealt with respect to the schedule, and I think we're going to be okay. Normally we would do some nice neat Van de Graaff demos and then an electric field lab and then do the basic electric field problem solving. Hey, we're just going to flip it, and at home with no school going on, we're going to get you going on the homework, and then we'll have fun with the labs and so on early next week. Don't forget, simple harmonic motion quiz on Friday, and we'll go from there. All the scheduling stuff that's on Classroom that I posted the last couple of days before they canceled school. By the way, tonight it's right now Tuesday night about 7 o'clock. All that schedule junk that's on Classroom, those earlier posts, chuck it out the window. Going to try to keep you going on homework the rest of this week, and then we'll go quiz Friday, then we'll be back in the lab. A little bit of homework Q&A probably on Monday, but I think this is going to get you far. I'm going to try to keep this to, you got 2 videos, right? 10 minutes on this one to lay out Coulomb, and then I'll do maybe, a second one that actually works a couple examples, hopefully keep that to under 10, and in 20 minutes you're going to be pretty much an expert on Coulomb's law. Alright, here we go. Thanks for your attention. I am actually going to start the Coulomb lecture with an old friend, mm/r², Newton's universal law of gravitation, 6.7 by 10 to the negative 11 Newton meters squared per kilogram squared. This is fast. I won't talk this fast through the whole thing, but this is review. Alright, this tells us a couple of things. The universal gravitation is inverse square. Let's draw 2 blobs. This is physics. We like pictures. Separated by a distance. Get the old red going on. This is what 2 exerts on 1, and what 1's going to do back to 2, obviously, is equal and opposite, as prescribed by Newton's third law of motion. So it's inverse square. Second, we think of gravity as a big force, but in reality, it takes giant masses to make a noticeable force, because this is 6.7 100 billionths. I had to think about that. Coulomb's law works the same way. Coulomb's law. Okay? It works the same way. Here's a blob of charge. Here's a blob of charge. Let's call this Q1. Let's call this Q2. They are separated by a distance r. They're going to pull. You saw that in lab. Of course, you used fur and stuff like that. This is the electrostatic force 2 exerts on 1, and of course 1 will do the exact same thing on 2. The equation. F is K Q1 Q2. Remember, from today, this represents charge. Q represents charge in coulombs. Over r squared. We're going to box that. Give you the Coulomb constant. It does equal something a little more fundamental. We're not quite there yet. Let me give you the number. 9 by 10 to the positive 9 Newton meters squared. I'm kind of looking up here to guide. Newton meters squared. Up here, with universal gravitation, mass gives rise to gravitational force. Here, charge gives rise. So it's not going to be per kilogram squared, it'll be per Coulomb squared, because Coulomb are the units we use to quantify charge, variable Q. What does this say? This says when you have a little bit of charge, even a little bit of charge multiplied by 9 billion makes a noticeable force. Okay? This is a much stronger fundamental force in nature than is that. Okay? Couple of interesting little rubs though. Mass is mass. There's one flavor of mass as far as this course is concerned. I'm going to get into dark matter and stuff. I wouldn't be the person to teach that. Okay? But with charge, you can have like charges. For that matter, it could have been a negative and negative, and you would have felt the same thing. These are two different pictures, right? Opposites attract, likes repel. Now, there's a whole bunch of ways. How do you account for positive and negative? Here's what I do. I just put a big old absolute value around these charges, and I don't even care about the signs. If they tell me this is negative 3 microcoulombs and that's positive 4 microcoulombs, I just go 4 microcoulombs and 3, okay? I use the picture to tell me the direction. I don't worry about plugging in negatives there, okay? Alright, so that's the only difference between the format of gravitation and Coulomb. Alright, we're on the home stretch here. Last thing I'll ask you about is why the R². And we reviewed it in class today, went back to here, universal gravitation. Why is it a square in inverse square? Here's this blob. This blob has an influence that radiates out into space in 3 dimensions. We can see 2 of those dimensions because I've got a 2-dimensional piece of paper. Okay? Imagine a negative charge here getting tugged on. But that would see the same tug as a charge here, as a charge here, as a charge anywhere this distance r away. If I now double that distance or triple that distance, remember, these fingers of force radiate out to infinity. Okay, radiate out into infinity. And even out here, okay, this charge would still get tugged on by this big positive blob in space. This is kind of like the planet now. Okay, the problem is that the influence of this charge, and it's the same charge with the same influence, now has to cover a spherical shell that is now triple the radius, or this being the surface area of a sphere, now 9 times the surface area. So this influence out here it's the same influence, but it's got to cover 9 times the area. Done. Alright, hey, the next one we'll do some examples and you're done.